This example is actually a revisit of a previous example where we have this sawtooth forcing function acting on our spring mass damper system, and we're trying to find the total response of our system. So everything is going to be the same, our parameters are the same, the sawtooth function is the same, but our solution method is going to be different, as now we're going to use the aggregate method to solve it, rather than doing the Fourier series expansion like we did previously. So we can dive into our modeling step first, and a lot of the information is already given to us like the last time we had this. So we already have the m, the c, the k, so we don't need to worry about doing Lagrange's equations because it's provided. So Newton seconds per meter, 220 for c, and k is 4,000 newtons per meter. And the general model of what's happening, we have this spring mass damper system with forcing acting on it. And we have already our equivalent m, we have our equivalent k, and we have our equivalent c. So we are looking for x of t. So find, we want our x of t. All right, so we have MCK, so F is now what we need to work on because we are only given it graphically. So the way we wrote it last time is we said, okay, well, this is a periodic function that repeats every 5 seconds. So for 2 seconds, it dwells at 0, and then for 2 to 5 seconds, it dwells at 500 newtons. So we wrote it out for just that fundamental period, that 5 seconds, that was 0, for t less than 2, and it was 500 for t between 2 and 5 seconds. And we did the Fourier series expansion on this. We found the coefficients, and then we used the methodology where if we know all the coefficients of it, we can find all of those particular solutions. And it worked pretty well, but we got this infinite series as our answer. We're going to do this one a little bit differently because we're going to use the aggregate method. But with the aggregate method, what we're going to have to do is we have to take each part of our piecewise function and keep adding on to it in subsequent pieces, which this doesn't do yet the way I have f of t written. One, it's only good for 5 seconds, which is fine for the Fourier series method. It's not fine for the aggregate method. So I need to keep defining this on different intervals. I'll just do it for a couple of these since it's going to keep repeating and we're going to get the idea. All right, so I'm going to rewrite this a little bit now. All right, so actually the first one is still okay, that this is good for t less than 2 seconds. But now for the aggregate method, what I need to do is I need to copy everything from the line above and then add another force to it. So this one is actually not too hard to write. So once we get to 2 seconds here, until 5 seconds, I can write that as 0, the line above, plus 500. And for consistency, I'm going to say that's 500 times, I'll call it h times t minus 2, just so we can have it in the right format that we're looking for. So 500 times Heaviside, which is the step function. So once 2 seconds kicks in, h of t minus 2 is going to equal 1, so it's going to turn on that first 500. And we know from the aggregate method how to deal with step functions. So I'm writing this as the sum of really 2 step functions. The first just has a magnitude of 0, and then a second one will turn on at 2 seconds, and it will take me to 500. So on this interval, 2 seconds to 5 seconds, that second line is going to evaluate to 500. But again, I'm just writing it in a very specific way. Now for the third interval, so I've covered 0 to 2 seconds, and now I've covered 2 seconds to 5 seconds. And so I guess technically that's open. So now I need to cover 5 seconds to 7 seconds. Now I know it's just going to equal 0. But again, I need to follow this format where I copy everything from the row above it and I add on another function. So I'm copying that 500 times Heaviside of t minus 2. And I know that this needs to sum to 0 because I know it is 0 on this entire interval. So what I can do is, in this method, I can turn a function on but not off. So I actually need to add another function that counters that 500 times the Heaviside function. So what I can do is I can subtract 500 h of t minus 5 for that third interval from 5 seconds to 7 seconds. So if we see what's happening, I have my first function that turns on. Now it's 0, so it doesn't really matter. Then at 2 seconds, my second function turns on. I step it up by 500. But then at 5 seconds, I turn on a third step function, which now is a negative 500. So I have 500 minus 500 brings me down to 0, but again, written in this specific way. Okay, so at 7 seconds, it's defined here. Technically, that's open. So now I'm on this fourth interval from 7 seconds to 10 seconds. So again, I will copy everything from the line above. And add another function. So for this interval, I'm back at 500. So I will add 500 t minus 7. Okay, so it's seemingly a more complicated way to write it, and it is, because I'm adding now this 500 times t minus 7 to it, to something that's already evaluated to 0. So it brings me back to 500 on this interval. So I won't keep writing it, but I can just keep repeating this process as many times as I want, because this function just keeps repeating itself. So we can get the idea here. Every time on the next interval, I'll subtract a 500 times an h of t minus 7. This should be an h here, since it's just turning on and off. Okay. And then on the next interval, I'm going to copy everything above, and then I will be adding a 500 times Heaviside of t minus 12. And then at 15, I'll do the same thing. So I do need to keep writing this over and over and over again. So for periodic functions like this, the aggregate method, I do need to keep repeating the pattern. However, in this one, because it keeps repeating exactly the same, it's not going to be too hard to assemble my solution for as many repetitions as I want, as we'll see in the solve step. So that's my f of t. It is identical to how I had it written before, in that it evaluates the same way as when I just wrote it as 0 or 500 for the Fourier series expansion. I'm just writing it in a very particular way here, as we'll see when we get to our solution step. So we have our modeling parameters. We have our f of t. We can write our equation of motion. So we're going to have mx double dot. We already know it's a simple spring mass damper, plus cx dot plus kx equals f of t as written above. So I won't rewrite that, but I can write this now with my values. 220 x dot plus 4000 x, all in base units, is f of t. And we see we have now our complete equation of motion for this system. And we have the identify step, which is really the same as the first time we solved this. We have 1 degree of freedom, x. It is linear. We have this general forcing, because the right-hand side is not just a simple harmonic motion. It's not just a sine or a cosine. It's more complicated, so we need to use something like the Fourier series expansion, or in this case, we're going to use the aggregate solution. And we're going to see that it is going to be damped. And we'll see what kind of damping we have, although we already know from the first time we did this. But for our solution, we want to make sure it's underdamped if we're going to use the methods that we've talked about so far in this class. So using the aggregate method, our x of t is going to be a piecewise function. It's going to be x1 of t on the first interval from t is 0 to 2 seconds. Then I copy everything above and add a second part. And that's good for this second interval for 5 seconds. And then copying everything above. And I have a third part of my solution for the third forcing. And here I do need to have t minus 2 in my evaluation. And this will be the t minus 2. And then the third part will be t minus 5. And that's good from 5 seconds to 7 seconds, and etc. Right, so in the piecewise, I'm going to have an x1, 2, 3, 4, 5, as many as I need for all of my cycles. And we'll do a couple of cycles here, but it's going to keep, the pattern is going to keep repeating of copying the whole solution from above and adding on that one more term each time that's going to coincide with the forcing term I have each time. So just so it's clear, this is my f1 of t is 0. I'll make this a different color so we can distinguish it. So 0 is going to be my f1 of t, and then my f2 of t minus 2 is this term, and then my f3, my f4, it's already that, and my f4 is down here, and then we can keep going if we have an f5, etc. Right, so those f1, 2, 3, 4 lead us to our x1, 2, 3, 4, depending on their form. So let's find some of the parameters we're going to need to solve this. And they're actually ones we've already solved the first time. Certainly our natural frequency, our k over m, root k over m, is going to be root of 4,000 over 10. And we get, once again, 20 radians per second. We can use that information to find our damping ratio, zeta, is c over 2m omega n, and putting in our known values that we were given and the omega n we just found, we get zeta is 0.55, so we already knew this was true, but we're underdamped. And we can put this together to find our omega d, since that's going to be our omega n times, for underdamped systems, 1 minus zeta squared, and the damped frequency 16.7 radians per second. All right, let's go back to the identify step. I made some more room here because we know what form our x1, 2, 3 are all going to take here, because looking back at our forcing, they are all step functions. The first one with a magnitude of 0, and then subsequent ones with a magnitude of 500, negative 500, positive 500, negative 500, etc. So x1, well, that's just a forcing of 0, so that is going to have no response. So that one's not very interesting. But our x2 is going to have the form of f over k, 1 minus 1 over root 1 minus zeta squared, e to the negative zeta omega n t times the cosine of omega dt minus phi. And that's just coming from our known solution when we have a step input. This is what the response is going to look like for that. Now, in this case, f is going to be the amplitude of that step input. So x2 corresponds to f2. Scrolling up here, f2 has a value of 500, is its amplitude. But if we look at f3, it's also a step function, but its amplitude is negative 500. So when we go down here to write x3 of t, everything from x2 is still going to be true. The k is the same, the zeta, the omega n, the omega d, the phi that we're going to find, that's the same. The only difference is that f is negative 500 instead of positive 500. So actually what we can do is take a shortcut in this one and say that x3 is just negative x of 2. Because all that's different is that f is equal to negative f. It's negative 500 versus 500. When we go to x4, that corresponds to f4. Well, f4 is a step input of magnitude 500. That's the same, except for the time delay is different, but everything else is the same as f2, which means that x4 and x2 are actually the same thing. So I don't need to keep rewriting it and resolving it each time. The only difference is going to be when I put that time delay in, x4 will kick in later than x2, because x2 starts at 2 seconds, and when we see up here, x4 won't start until 7 seconds, because that's when f4 begins. And we can keep going with this, that then x5 is just going to be also a negative x2 of t. then x6 is going to be x2 of t positive, and etc. So really we only one time need to figure out this x2 equation, and that's just positive and negative of that as we go on. So what I'll actually end up naming this is I'll just say that x on is x2 and x off is negative x2 of t when I go and solve it a little bit later on. And I still have this phi to deal with here, which is a parameter I can solve for. So I'll do that before I put together my solution. So my last parameter, phi, that is the inverse tangent of zeta over square root of 1 minus zeta squared, coming from that solution. And that will turn out to be 0.5824 radians. Now I can assemble it, and then I'll actually do the assembling and the solving once I get into MATLAB in a bit. So my total solution for x of t is this piecewise function, well, 0 for 0, t is between 0 and 2. Then it's going to be x on, well, I'll copy the 0 just for completion here. 0 plus x on t minus 2. And that was good for 5 seconds, 2 to 5 seconds. Then x on of t minus 2 plus x off t minus 5 from 5 to 7 seconds. And then from 7 to 10 seconds, it will be everything above. So I'll copy that. X on t minus 2, x off times t minus 5. And plus another x on t minus 7. And again, that will keep repeating. We'll do that in MATLAB. I'll do it for a couple more cycles there, but just copying everything I have before. And this gets me my total solution for x of t for this repeating pattern of step-ons and step-offs. So I have f1, 2, 3, 4. I will add more of those and see what the response looks like. Now, once again, we've already solved this actually 2 other ways, because we solved it not only using the Fourier series expansion, but we also used ODE 4.5 and got a solution that way. And previously we saw that our Fourier series solution, when we took enough terms in it, basically matched almost identically the ODE 4.5 solution. Let's see how this stacks up. Does it match our ODE 4.5, which we took to be the true solution, just for comparison? How does this third way of solving this line up? In the MATLAB now, I have my parameters that I will put in, and solving for those other parameters, natural frequency, zeta, omega d, just to check those values, zeta, omega n, omega d, those are going in correctly. And I do have the original forcing just to make sure I'm doing this correct. And this looks like what it did the first time at 0 up to 500 down to 0. So this I actually won't use in my solution, but just to make sure everything's going okay. And remember, I'm using that to plot that, to do this periodicity, I'm using that mod function with t to make sure that it keeps repeating itself every 5 seconds, since that's the fundamental period. Now we're using the aggregate solution here, so we're not going to need to mod it. It will take care of itself, but we do have to keep repeating and stacking the pieces on top of each other. All right, so really what we're after starts to come down here, solving the phi. So it's here, 217, what I am calling x on. All right, so that was that x, the same thing as x2. This is coming from applying that positive 500 amplitude step function. And this is the response from a step input, just like we saw on the slide, just like I wrote down by hand. And then I'm defining x off as just negative x on, because this is for every time I am applying a negative 500 amplitude step function, which then keeps repeating itself. So I can boil it down to x on and x off, which is the same as x on is really just the x of 2, and x off is the negative x of 2. So now I can assemble that total solution, which I have as a piecewise function. Now here I'm using that comb function, using this logical comparison. So really here I can say it starts with 0. It doesn't really do anything, but that way it's consistent with what we have before. So this is really the solution x1 for our f1, which was simply 0. It doesn't do anything. I add to that then, when I get to my second interval from 2 seconds to 5 seconds, I have this piece. So this piece here is where I add on that x2 of t minus 2. And that's what's happening here. I have x on of t minus 2 as defined above. But to adhere to the piecewise part, I don't want it to happen until 2 seconds has elapsed. So that's what this logical comparison is doing here. This has a value of 1 once I reach 2 seconds and 0 before that. So this x2 piece doesn't turn on until 2 seconds. But once I turn it on, I have no way of turning it off. So that's where I have now my x3 solution. And that corresponds to f3, where in f2 I applied that 500 step function. Now f3 was applying that negative 500 step function to cancel out or to stop that first one that I turned on. So that's where this x off or x3 is coming in at 5 seconds. Right, so I have that delay built in, and again I don't want it to begin until 5 seconds has elapsed. And then I go here, I have my x on t minus 7, off at 10, on at 12, off at 15. So I have here, I'm going for 15 seconds. I didn't write it all out by hand, but I can just keep adding these pieces of it for each of these cycles of forcing that's happening. So my x of t is good now for 15 seconds. If I wanted to investigate what happens longer, I would just have to keep adding the ons and offs for as long as I wanted to be able to get my solution. So let's plot the analytic solution so far. This is from the aggregate. So this graphically is what we get. So when there's no forcing, we're at 0. Then we apply that first 500 Newton step function, and it jumps up to 0.14 meters and then settles back down. So notice with this analytic solution, we don't have all of those artifacts, all of those false oscillations like we saw when we had only a few terms in the Fourier series expansion solution method for this. Right? So it looks very smooth, it's very flat during the dwells. So it oscillates, it overshoots, undershoots, and then pretty quickly comes down to being flat once that energy is dissipated. So at least visually, the solution looks good compared to at least when we only had a few terms in a Fourier series solution. But what we want to do is we want to compare this to another solution method just to make sure that they agree. If we can solve it multiple ways, it's sometimes a good idea so that we can be confident in the answer that we're getting. So for comparison, I am going to run my ODE45 version of my solution. This exactly the same as I did the first time I solved this. So that driver 5.2, just as a refresher, what that's doing, that's my state space model for this. And this is where I put together my state space model and I have my force defined here. So it's exactly the same driver I used the first time I solved this. So that's what I'm running for ODE45, and I'm running this also for that same 15 seconds. And I'll plot them on top of each other. So let's run the whole thing and see what it looks like. All right, so these are both on top of each other. Red is the ODE45 numeric solution, and black is the analytic solution, like I just saw. So visually here, from at least afar, they look identical. They're right on top of each other with very few differences. Let's zoom in so we can see if there's more detail. Really no differences by eye we can tell even as we zoom in. They're really right on top of each other. Now this ODE45 solution was done with pretty small time steps. I did define it here to use millisecond time steps. If I let ODE45 run with its kind of its choice of the time step to use, it might not look quite as good. So I did kind of bolster the quality, the precision of my ODE45 just to make sure it was giving me a good precise solution here. But visually, they're right on top of each other. a root mean squared error comparison wouldn't really help here to shed light on how close they are, because root mean squared error, the way we've been doing it, is really for looking for convergence. Does that root mean squared error approach some constant value, in which case we can say, all right, adding more terms doesn't make this any better. But this isn't, we can't really do that here because the analytic solution only had, it was that exact solution. There was no summation that we had to take. And with the ODE 4.5, it just spits out a solution, and we were taking that solution to be the true solution. So RMSE doesn't tell us much. It's really this visual inspection that's going to say, does this look good or not? And yes, this does at least visually look really good. The two solutions match each other. And thinking back to when we saw this the first time we did it, we also had that Fourier series solution where we used like 100 terms or 1,000 terms, and we saw that that too looked really, really close, really, really good compared to the ODE 4.5. So in the end, what we have here is our analytic complete solution. This time it's a piecewise solution, not an infinite series like with the Fourier series expansion version. But x of t we have an exact expression for with the types of inputs we have. In this case, we had those step-ons and step-offs, or a positive step input and negative step input. But largely the problem was the same as the first time we saw it. It was how we defined f of t changed a little bit, even though it still is identical. It still is perfectly matching that given graphical version of f of t, but writing it as this sum of adding one more term, one more term, one more term on each piece allows us to use this aggregate solution for x of t, where we solve f1, what's its response? What's the response from f2, from f3, from f4, and we make a piecewise solution from that. This one we lucked out because everything was a step function and it kept repeating itself. It was either the positive step function or the negative step function, on, off. So there wasn't too much in the way of the solution because it kept repeating. It was either x on or x off, and then with that built-in delay. So what we have to keep in mind is when we assembled our solution, we had to put in that time delay in each of our pieces as we went from one interval to the next.